All right, today we're going to be looking at average value in motion. This diagram that you see is actually the same diagram you're going to be using later on in a problem set. I just wanted to expose it to you early on so that you could kind of get a look at it. So we have dealt with average rate of change quite a bit. And so we're going to leverage this idea of average value from what we've been doing, which is signed area under the curve, as well as average rate of change. So let's just deal with something we've had done already. So looking at this graph, notice my units are feet per second on the y-axis and seconds on the x-axis. So to better understand average value, we're really going to leverage those units. So first, let's look at average rate of change, which we've seen quite a bit this year. And remember that we built our idea or understanding of instantaneous rate of change as the limit as h goes to 0 of the average rate of change. And so if we're looking at an average rate of change for this diagram, notice this is a function of velocity. So we would have v of b subtract v of a all over b subtract a. Now I kind of want to, before we put numbers in, I kind of want to get an idea of what the units look like here. So if we were just breaking this down with the units without any actual values in for v of b and v of a, we would have velocity, which in this case is feet per second, subtract feet per second, another velocity, all over seconds subtract seconds. So we would have seconds. So we're going to have, I'm actually going to write it like this. We would have an expression for velocity in feet per second all over an expression of time, which would just be in seconds. And so if I were to just simplify this fraction by multiplying by seconds over seconds, I would end up with feet per second squared. And I know, and you guys know from taking physics, that these units represent an acceleration. So if I'm finding the average rate of change of a velocity graph, it means that I'm actually looking at acceleration, right? So I'm finding the average acceleration of that graph because I'm finding the average rate of change, and the rate of change of velocity is acceleration. So this is giving me an average acceleration. All right, so now let's look at an example with that. So if I wanted to find the average acceleration, given a velocity graph, on the interval, let's go 0 to 5. Actually, let's not do that because I think I'm going to have you do that later. Let's go 0 to 3. So the average acceleration between 0 and 3. So we would say, all right, that means that we're doing v of 3 subtract v of 0 all over 3 subtract 0. So v of 3 is up here at 4. V of 0 is 0 all over 3. So we would get 4/3. And again, this is meters per second, or I'm sorry, feet per second in this case, divided by seconds. And so we're talking about feet per second squared. So the average acceleration between 0 and 3 would be 4/3 feet per second squared. All right, now our new piece of info is what's called our average value. And our average value allows us to find the average of a function that we physically have in front of us. So where this example up here was our average rate of change, and as a result, my average acceleration given a velocity graph was what I was able to find. Now I'm going to be able to find the average velocity given a velocity function or velocity graph, which up until this point we haven't been able to do. If I wanted average velocity, I had to leverage the position graph or a position function. If I wanted average acceleration, I needed to leverage the velocity graph. We always had to work one behind. Now we can look at a graph that we have a velocity and actually find the average velocity. So our average value function or average value formula is going to be 1 over b subtract a. times the integral from a to b of f of x dx. So to take this, so this is our average value function, to take this and apply it to average velocity given a velocity graph, it's simply going to be 1 over b subtract a times the integral from a to b of v of t dt. Similar to what we did before, let's just take a look at our units to see how this breaks down. So 1 over b minus a, well, we talked about before that b subtract a is in seconds. So if we're looking at our unit breakdown, this first expression is 1 over seconds. Now, when we're working with our integral, as a reminder, what's happening here is I'm finding area, signed area under the curve. So when we've been calculating these, we've just been finding area, right? So my velocity is in feet per second, and my dt is in seconds. So what we've been doing to find that is we've been multiplying our velocity, so whatever the height of my function is, times that infinitely small width, but even though it's infinitely small, it's still in terms of seconds. So we've been multiplying feet per second times seconds. And again, we've just been adding all of those up. So if we take a look at this dimensional analysis, my seconds cancel out, right? And so I'm left with feet per second. So this function is talking about an average velocity because the units I get out for that are actually velocity. So let's go ahead and do that same example, but now with finding the average velocity instead of the average acceleration. So we're going to do the same example. This time we're going to find the average velocity over the interval 0 to 3. So my average velocity, I'm just going to say v and then average, equals 1 over 3 subtract 0 times the integral of 0 to 3 v of t dt. So I have 1 over 3 times, and now I'm going to go up to my graph. I'm looking at the signed area under the curve right here. I'm going to break this up. So I have a rectangle that's 1 unit by 4 units, so that has an area of 4. And then I have a triangle that's 2 units by 4 units. So that's going to be 4, because 2 times 1/2 gives me 1 times 4. So I get 4 there as well. So I have 1/3 times 8, which equals 8/3 meters per second. All right, so notice this difference here. I have my average acceleration. I used the same graph to find both my average acceleration and my average velocity. We just had to find that in 2 different ways. All right, now what we're going to do is just see what else we can leverage with this graph since we're working with it, and it's stuff that we've seen before, just not with integrals. So one key piece of information that you'll notice is that x of 0 equals 12. And so I'm just going to go ahead and write that down. That means that at time 0, I'm already 12 feet away from my starting point, right? Or 12 feet away from wherever. I've already traveled a distance of 12, whatever that may mean. And so now we're going to go ahead and we can find a couple of different things. We're going to find the position at 3 seconds. We're going to find the displacement, or another word we might see this is net change over 0 to 3 seconds. And we're going to find the total distance traveled over 0 to 3 seconds as well. All right, so position at 3 seconds. In order to figure out the position, we need to know how far we've already traveled because we need to know where we're starting from. And then what our integral is giving us is whatever that displacement is after that point, right? So we're going to say, okay, I'm starting at 12. So it's going to be x of 0 plus, actually, let's write it like this. X of 3 is going to equal x of 0 plus whatever that distance is that I traveled between 0 and 3, which is just the integral of v of t from 0 to 3. Because remember we talked about when we first introduced antiderivatives, when I had derivatives, the derivative of position was velocity, the derivative of velocity was acceleration. So now if I'm working in the inverse or the reverse direction, if I'm starting at velocity and I want to get to position, I need to take the antiderivative because we're just doing the opposite, we're undoing. And so for this one, we'll have 12 plus, and we found that this right here, this integral from 0 to 3 of v of t dt was 8. So 12 plus 8, so we'll know that it's moved, or it's at the position 20 feet at 3 seconds. When we're talking about net change or displacement, that's just this piece right here. So the displacement over 3 seconds is going to be equal to the integral from 0 to 3 of v of t dt, which is just equal to 8 feet. And then lastly, our total distance traveled, because I was always moving to the right, because my velocity was always positive, my total distance traveled is actually going to be the exact same as my displacement on the interval 0 to 3. But the way that we calculate this is a little different. We say 0 to 3, we're doing the absolute value of v of t dt. And so what that results in is any time that I am below my curve, I just need to take a minute and make that signed area positive, because essentially what's happening, if you look up at your graph, is we're going ahead 1 2 3 4 1 2 3 4, and we're going ahead and we're essentially going like this, and we're forcing that to be above our curve now. And so what that allows for is all positive area to be added up. Sorry, that's my printer in the background. And so for this one, because it was already all positive, we're still going to get 8 feet. But if we had gone from 0 to 9, then we would have had to take this whole negative signed area and just made it positive. And you'll do that in your next problem set. All right, so I hope that helps. Again, average value is, I'm looking at a graph of acceleration, let's say. If I want the average acceleration, I'm using this formula right here, but I'm putting in a of t dt and finding the average acceleration that way. If I want average velocity and I have the graph of velocity, I'm simply using the graph that's in front of me and this formula, and it tells me exactly what the average is for the function or graph that I have in front of me. If I need to go to if I have velocity and I want average acceleration, then I'm using my old school, right, average rate of change formula. So that's kind of the big difference. We have average rate of change, which is that just traditional slope formula that we've been using for a while now. But now my average value allows me to leverage the graph or function I have in front of me to find the average of that function. All right, have fun. Good luck. Sorry I can't be here. And I will see you guys tomorrow.